patterns. First one is the conjugate product pattern. If you multiply, we've already sort of talked about this earlier in the year. If you multiply two conjugates together, what's it mean to be a conjugate? It's right. The same different operations between the two terms. That's it. One you're adding in one case and subtracting in the other. That's it. So something of the form a plus b times a minus b, or vice versa. Doesn't matter. Either way, you get a difference of squares. A squared minus b squared. Okay, so there's one pattern. We're probably already familiar with that one. You can fill in some blanks on some of these other ones too. For example, you can tell me this one. What's a plus b quantity squared? A squared plus, yeah, you got that one, right? We know that one, okay? That's a handy one. We want to go we want to memorize up through cubic binomials. And the next one, it's easy. In 10 seconds, you'd have it memorized. But I want to show you a trick. There is a formula called the binomial theorem, which tells you how you can take any power you want to, and you can come up with all the terms in that expansion. At some point, maybe at the end of the year, we'll go through and take a look at that, because it has some implications about statistical stuff too. But for now, it's kind of hard to remember, and it's not one that you'll probably always have to look it up. I can never remember what it is. But there is a trick for relatively small numbers, exponents. There's an easy way to come up with all the coefficients. Pretty easy. It's called Pascal's triangle. Okay, Pascal's triangle, here's what it looks like. Pascal's triangle, you're going to start off with a 1 at the apex of the triangle, and then you're just going to, the slopes of the triangle are always going to be 1s, but then any interior number is just going to be the sum of the two numbers above it. You get the trick? See the pattern? So that's a 1, that's a 1, that's a 1, that's a 1, that's a 1. We could fill in a bunch of 1s. These are all going to be 1s here, right? But the interior numbers are built by adding up the two numbers above, to the above left and above right. So 1 plus 1 is 2. What's that going to be? 3, 4, 5. And you get the idea. We could keep going, right? So what? What does all this stuff mean? So Pascal's triangle, what this is giving us, these are giving us the coefficients of the terms in the binomial, successive binomial expansions. So whatever the row number is, we're starting with row 0, that's going to be the exponent that goes with the binomial. We'll just use a plus b, right? And a can be anything and b can be anything. But what this is telling us here, let's just look at these each one at a time. So this is telling us that a plus b to the 0 equals 1. Big deal, right? We know that. This is telling us that a plus b to the 1 equals 1. Let's do it this way. Equals 1a plus 1b. Big deal. We know that too, right? Here's where it starts to maybe get a little more meaningful. This is telling us here that a plus b squared equals, the coefficients are going to be 1, 2, and 1. Okay, what goes with the coefficients? Here's the other part of the pattern that really hasn't been a big deal so far. But whatever this exponent is, the product of a and b in each term has to have an overall power of that, right? Like in this case, we had a to the 1 times b to the 0. We don't write the b to the 0, but it's there. Plus b to the 1 times a to the 0. A to the 0 is just 1 though, so we don't write it. Agreed? So what's going to be here? Well, we're going to start with all of the exponential weight shifted to the first term, which is a, and none of it is with b, and then incrementally we're just going to step the powers of a down by 1 and the powers of b up by 1, so the sum of the two exponents always remains 1 in this case or 2 in this case, right? So we're going to get 1a to the 2 times b to the 0 plus 2a to the 1 b to the 1 plus 1a to the 0 b b, it's getting kind of scratchy, b to the 2. Okay, you get the idea? So you tell me then, what's going to be the expansion for a plus b cubed? The coefficients are going to be 1, 3, 3, and 1. And what are the powers going to be? Plus. Okay, plus. Plus. That make sense? Okay. And we could go down to any one of these, like we could take this guy here, for example, if we wanted to, and let's just put the powers of A and B in there. That would just be 1 a to the 5th, right, plus 5 a to the 4th b plus 10 a cubed b squared plus 10 a squared b cubed plus 5 a b to the 4th plus 1 b to the 5th, right? Get the idea? Now, we don't need separate, sometimes books will show you separate patterns for differences rather than sums, but that's not, we don't need to do that, right? If we want to do something like, for example, what if we wanted to expand out, let's say, 2x minus 3 to the 4th? Okay, we can do that. What's a in this case? 2x. What's b? Negative 3. Right? We're just adding a negative 3. See what I'm saying? So then we get the coefficients. We're on row 4, aren't we? So we get the coefficients 1, 4, 6, 4, 1. Right? And we're going to get, here we're going to get what to the 4th? 2x. The quantity 2x, which we'd have to simplify, right? Right? So that's going to be, what, 16x to the 4th if we simplified that. Okay? Plus 4 times 2x cubed times negative 3. Okay? So that's going to be a negative term, isn't it? Because I've got a negative 3 to an odd power. Plus 6 times 2x squared times negative 3 squared. So that's going to be a positive term because negative 3 squared is positive, right? Plus 4 times 2x times negative 3 cubed. So that's a negative term. Then finally plus negative 3 to the 4th. Right? And then we just simplify each term. Okay? But no big deal. All right? So there's a little trick for, that's reasonable to do up through probably rows 7 or 8. It's pretty easy to just crank out a Pascal's triangle if you ever need to, right? Rather than have to memorize that binomial theorem. Okay, what do you notice here? I just want to point something out. What do you notice about that triangle, about the coefficients? You notice any, what can you tell me about the symmetry?
The second middle row, second back.
Say it again, Seth. Say it again.
They peak in the middle and it's symmetrical going down.
Okay, so yeah, so you see that you could kind of think of it, we could sort of draw maybe a line of symmetry down the middle of this thing. And the expansions, all the expansions are going to be symmetrical about that midpoint, right? Now, let's just think, and this kind of stuff for you, class like yours, you guys are so smart. I want you to think about this in a way. It has to be that way, doesn't it? Right? Because is there anything special about A and B? I mean, we know that addition, if we go clear back to the start of the year, we know that addition is associative and commutative, right? It doesn't really matter the order in which I add things up, agreed? You get what I'm saying? So I could just as easily say B plus A to the n. And so the math gods are wise, right? They know that the coefficients have to be symmetrical because it has to be insensitive to flipping the A and the B around. You get that? If I flip the A and the B, I shouldn't get anything different, and I don't, right? It has to be consistent with the associative and commutative properties of addition, right? So it all kind of comes full circle. I like that about that. What's that? So, we don't even probably need to, I'm going to skip this stuff with you guys. You guys can do this. I mean, you just tell me, what's A and what's B here? Well, here, let's do 1. That's a short one. Let's do 1 real quick. So what's this gonna look like then? It's 2, so the coefficients are 1, 2, 1, right? So we're gonna get 1 times 10x squared, good, plus 2 times 10x times -1 plus -1 squared, good. And if we simplify all that, that's just gonna give us 100x squared minus 20x, right, plus 1. Okay, good. So I think we're done with that stuff. You can deal with that, no issue. All right. The thing I do want to show you today that's a little heavier duty